Okay. Looks like it works now. Okay, sorry about that. Somehow didn't want to work at the beginning. So if we have some string with pulse on it, which is moving from left to right. So here we have some firmly fixed edge of the string. And here, for instance, we have some attached mass. Then when the pulse will come to this point where the mass is attached, we will see that this mass will move upwards from the initial position, so along axis y. And that means that there will be some work done because of moving this mass in the gravitational field of Earth. So means that obviously mechanical waves, they carry some energy, and our goal is to understand how to quantify it. So if we consider such a model case, let's say we have here y-axis and some attached simple harmonic oscillator to a string. So it creates some sinusoidal wave, and we should consider a small element of the string with length dx, and it will possess some mass dm. Okay, so we have such a model, and let us focus on its kinetic energy. So we know that kinetic energy is defined as 1/2 of mass times v squared. In this particular case, we will consider speed v along axis y, because along axis x, we know that there is no displacement of any element of the string when the wave is propagating along the axis x on the string, but it always moves up and down. So any element of the string will move up and down along axis y. So here we consider y component. So if we apply for this particular small element of the string, we can write dk, like small kinetic energy, 1/2 times dm times, we can specify vy squared, so which highlights that this motion happens along axis y. So also what we can define, dm would be equal to linear density, assuming it's uniformly distributed along whole string, times dx. So we eventually get dk for this kinetic energy of a small element of the string equal to 1/2. Here will be mu times dx instead of dm, and here will be Vy squared. So as you remember from our previous discussions, we derived expressions for speed of the elements of the string based on the wave function, which we took first derivative of y, like first partial derivative of y over dy over dt. So wave function is y, displacement along axis x as a function of position and time. So velocity along axis y could be given as dy over dt at x equal constant. So it's partial derivative. So we already did that, and we got the following result. So velocity, like this, speed of the element of the string is equal to minus omega times amplitude displacement, and along axis y times cosine kx minus omega t plus phi. So we assume that phi, this initial phase constant, is equal to 0. And then we can substitute this expression for speed here in the expression for the kinetic energy. So let us do it on the next slide. So we can write that small kinetic energy of this small element of this string is equal to 1/2. Now there are some delays. 1/2 times mu times this v square. So we will write the expression minus omega times a times cosinus kx minus omega t. So we assume that phi is equal to 0. So here we close this and put it to the second power. So it's instead of v squared. And here we also need to add dx. So we can make one additional step in order to make our life easier, to get rid of time. Let us pick up some moment of time t equals 0. Then we can write for this kinetic energy as a function of position already. 1/2 times mu times omega yeah, maybe not. Let us first take this second power. So it will be 1/2 times mu. Then it will be, we will get rid of this minus because we have it in second power. So it will be omega square times a square times cosine square times kx minus omega t and times dx. Okay. So now let us get rid of this time, assuming that time is equal to 0. So we consider just some moment of time as a initial moment of time, t equals 0. So in that case, kinetic energy can be written as follows. It will be 1/2 times mu times omega square times a square times cosine square, and here we will have k times x dx. Okay, so that we have expression for kinetic energy for a small element of the string as a function of position of this small element, because here we have this x at a given moment of time t equals 0. So now let us calculate kinetic energy of all small elements of the string along one wavelength. So let's mark it as k lambda equal to integral from 0 to lambda dk. So understand what we do. We have many small elements along axis x, and we consider one. If we come back here, yeah, let's say this is axis x. So, and this is, if this is 0, this is lambda, one wavelength. So distance between adjacent points with the same phase. And we have many of these small elements along the one lambda distance along axis x. And that's why if we now integrate for all of them, we will get total kinetic energy, what this string is carrying at a distance, this wave is carrying at the distance of interval of 1 lambda. So in order to do that, to sum up it, we need to integrate from 0 to lambda over x. And we can write it as follows. So here we have in this expression for dk, we have a bunch of constants. And actually all of these will be constants. So we can write them in front of the integral, 1/2 times mu times omega square times a square times integral from 0 to lambda. And here will be cosine square kx dx. Okay. So we need to take this integral, and it's actually not so straightforward because we need some trigonometric transformation in order to deal with it. So from the geometry, we can write that cosine square x would be expressed as 1 plus cosine 2x divided by 2. So in this case, if we have kx, so it will be the same, but we will have this wave number k in our argument. Okay, so keeping this in mind, let me delete this. We can get actually two integrals out of this one. So it will be, here are our constants, 1/2 times mu omega squared times a squared. Then we have 1/2 integral from 0 to lambda dx, because there was unity in the numerator, 1 divided by 2. And then plus 1/2 integral from 0 to lambda cosinus 2k x dx. Okay, so now let us focus on these two integrals. So that will be equal. Let's go to another slide. So k lambda is equal. Again, we write down our constants, which will be 1/2 times mu omega squared a squared. Then we will have first integral will give us x over 2 from 0 to lambda plus here what we had, if we look back, we have 1/2, and we have in the argument of the cosines, we have 2 times kx and dx. So we need to modify our differential in order to match the argument of the cosines. And that's why we need to divide and multiply. So we will have d2kx, but in order to keep everything the same, we need also in front of integral get 1 over 2k. And then when the differential and argument of the function will be the same, we can integrate. So that's why it will be 1 over 2, which we had before, then times 2k integral from 0 to lambda cosinus 2k x d2kx. Okay, now we can easily integrate this. So we will have 1/2 mu omega squared times a squared. Here will be, if we substitute already these boundaries, it will be lambda divided by 2 for first integral, then plus it will be 1 over 4k times sinus 2kx, and that will be from 0 to lambda. Okay, again, we write here our constants. Here will be lambda divided by 2 plus, if we substitute here these boundaries, then we will get 1 over 4k times sinus 2k times lambda. Okay. Any idea what will be equals this sinus 2k times lambda? Do you have some suggestions? Do you remember what is? No, it's not in terms of trigonometric transformation. I mean numerically. What will be equal sinus 2k times lambda, or sinus k times lambda without 2, doesn't matter. If you remember this wave number, when we introduced this, it was k is equal to 2 pi divided by lambda. So now if we have k times lambda, that will be 2 pi over lambda times lambda. We cancel it out, will be 2 pi. And sinus of 2 pi or any pi will always be equal to 0. So means this second term in the parentheses is equal to 0. So eventually we will get that kinetic energy of a wave at the distance of 1 wavelength will be equal to 1 fourth mu times omega square times a square n times lambda. So here we see already kinetic energy contribution, kinetic energy component of energy transferred by a string. And if we do similar analysis for potential energy per unit length, we can write u lambda. That would be also equal to 1 fourth mu times omega square a square times lambda. So that's why if we consider whole energy of a wave per 1 wavelength, it will be 1/2 mu omega square times a square times lambda, since we that is equal to k lambda plus u lambda. So we see here that several parameters influence on the energy which is transferred by the wave. So here is parameter mu, which defines properties of the string. It can be heavier, like denser per unit length, or lighter. That matters. The denser, if we keep, for instance, amplitude the same, that like denser string will provide higher energy. That's why, for instance, if we have some interface between two strings, and if we create, so this situation which we discussed previously in our previous discussion, if we create some wave or pulse in the same string, then it is transferred to the interface. Part of its energy is directed towards the reflected pulse, which goes back with the opposite phase because the interface is approached from the lighter string, where the speed of propagation of the wave is higher than in the other side, in the heavier string. And then there will be some transmitted wave. So the thing is that transmitted wave will possess smaller amplitude because this mu will be higher. So if mu is higher, and then let's say some energy which is transferred is defined like fixed, then in order to transfer the same amount of energy, we will reach lower amplitude because mu is higher. Then they all energy is proportional to mu and square of the amplitude. So we see that amplitude actually is more dominant parameter because in second power, so it will define energy transfer by the wave, kind of influence on the amount of energy transferred by the wave more than density of the string. However, both of them make a difference. And now our final step here will be to determine what is the power transmitted by the wave. So means amount of energy per unit time. And this as unit time, since we know amount of energy per lambda, and we know it takes period of wavelengths to move the distance, which is equal lambda wavelengths. So that's why we need, in order to determine the power transmitted by the wave, we need to divide this E lambda by period of the wave. And that will give us power, energy per unit time. So power of a wave will be energy per one wavelength divided by period. So that will be equal to 1/2 times mu times omega square times A square times V. So we see that also with, so this V we made, before we make this substitution to make it more clear, here we had lambda divided by T. So we know that V, speed of wave propagation, is equal to lambda divided by period, because it moves lambda distance per time, which is equal to period. So that's why instead of this lambda divided by T, we can substitute speed of wave propagation. That's why it will be equal to 1/2 times mu omega square A square times V. So what do we see from here? That power, which is transferred with a wave, means energy per unit time. Will increase with omega, with angular frequency and amplitude in square. So these are most dominant parameters. And also, if we have medium with higher speed of wave propagation, that will also increase the power which is transferred by the wave. So, summarizing our work today, we were trying to derive the equations for energy transferred by the wave. So we considered some small element of the string, considered its kinetic energy of this small element of the string. Then we integrated. There is a question, is that velocity on the right? Yes, it's v. It's speed of wave propagation along axis x. Then we determine the kinetic energy. You're welcome. Kinetic energy per unit wavelength, which was achieved by integration along axis x from 0 to lambda. We didn't derive that explicitly, but if we do similar procedure for calculating energy, potential energy per unit wavelength, we get the same expression. So we actually, when we sum up kinetic and potential energy per unit wavelength, we get just twice more than kinetic energy we derive. And then in order to determine the power, means energy per unit time which is transferred by a wave on a string, we divide this total energy which is comprised by this wave per unit length divided by the period of the wavelength, and that gives us energy transferred per unit time. So we end up with this equation, which I would recommend to remember, which is 1/2 times linear density mu of the string, two most influential parameters, omega square and a square, so angular frequency square and amplitude square, times v, which is speed of wave propagation along axis x. So that could be required in solving some problems related to energy transferred by waves. So please remember this equation and be ready to use it in some application. Okay, so I guess this is everything what I wanted to tell you for today. If you have any questions, you're welcome. Yeah, we will proceed further with a new topic on next week. So I believe it will be sound. Yeah. So we will consider in more details is longitudinal waves, which are sound waves in atmosphere, and define some basic properties of sound waves. Okay, thank you very much for attention. Then have a good day and see you on Monday.
Thank you. Goodbye.
Yeah, and have a good weekend. Bye-bye.
You too.